Hello and welcome to the next installment of Momentum, where we are going to look at impulse. And we're going to start thinking about objects as a system. And impulse is an important concept when it comes to thinking about objects interacting and that system. So the definition of systems and of impulse, this is a definition I'm going to give you for what it means, but it's not something you would find anywhere per se, but it does explain what it is in words. Usually if you look this up, you'll just find the formula if you look for a definition of impulse. But I'll tell you what it actually means. It is the impulse is the amount of momentum imparted in an exchange between bodies. So there is some interaction of bodies, and there's an exchange of momentum when those bodies interact. And the impulse is that amount of momentum that's imparted to one from the other. And the reason it's called impulse is it comes from the Latin impulse pressure. So if you picture two bodies interacting, one would be exerting a pressure on the other one, or a push, a pellera, push on it that would change the momentum or change the velocity of the other object. Now the formula is J equals F bar delta T. Now the J, of course, is the impulse. You might find if you look, you would see that in other sources you might see, I'm doing this dotted, that impulse is I. This convention I will use is J, but I you will see just as frequently as J in this particular case. It is a vector quantity. We have time, which is the period of interaction measured in seconds. F is the average force measured in newtons. Abbreviated as a capital N. So that's the average force in newtons. Now I'll tell you also that a newton is kilogram meters per second squared, but we will just say newton in this particular case. And that means then that the units of impulse are newtons times seconds, or newton seconds. And for now, we'll leave the units there as that. Oh, so let's take that. Let us go further ahead with these units. So if we have units of force, which are kilogram meters per second squared, and we have time, which are units of seconds, so this is F and delta T, then you can see this seconds and this seconds will cancel, and we'll be left with kilogram meters per second, which you will recognize as MV. So MV is momentum, of course, and the units are kilogram meters per second. So kilogram meters per second and Newton seconds are equivalent units. That's just something to know now, and you'll see why later that could be important, but just something I'm giving you that information right now. So let's take a look at the impulse imparted. We have a cart traveling on a track, like so, with our positive direction and our negative direction. So we've got our car like this. It is traveling at 2.00 meters per second, and it's got a mass of 1.0 kilograms. An observer gives it a push. So someone comes in. So we're dealing with two different times now. So we'll draw that person's hand, giving that cart a push. And after it gives that cart a push, it is now traveling at 3 meters per second. So what we see is that the person, gave the cart an impulse. So let's find out our initial momentum. So P0 equals mv. We've got 1 kilogram times 2 meters per second, which is going to be 2.0 kilogram meters per second. That's our P0. And our P is going to be mv, 1 times 3, or 3.0 kilogram meters per second. And of course, the reason I'm reporting 2 significant digits is that the mass has 2 and the velocity has 3. So now we want the delta P. Well, the delta P is m delta V. We'll actually do the simplest version is P minus P0 is 3.0 minus 2.0, which is 1.0 kilogram meters per second. And it's a positive. So the change in momentum, and of course, given this frame, you can see it's got more, the frame of reference, it's got more momentum in the positive after this interaction. We could have also done a delta P as m delta V, which is 1, and then 3 minus 2, which would give us 1.0 kilogram meters per second. So whether we find the initial momentum, the final momentum, and then calculate it this first way, or we go straight to this, we could see this, of course, we could do it all just in one fell swoop. But if we need, for some reason, the initial or the final momentum, we would do it this way. So I'm just showing you both ways for that purpose. So what's the change in momentum? We have our change in momentum. And what impulse did it receive? Well, let's see. The impulse it received is 1. So the impulse it received is also 1.0 kilogram meters per second. And if you remember that definition I gave of what impulse is, it's the amount of momentum gained by a body during the interaction with another body. Well, that amount it gained was 1 kilogram meters per second, or we could say 1.0 newton second. Now, of course, you can see then that the reason that momentum changed is because a force was applied for a certain amount of time, and that brought about a change in momentum. That change in momentum being equal to the impulse that was imparted. All right, so what impulse did it receive? What is the rate of change in momentum? What is the rate of change of momentum? So delta P over delta T is the change in momentum, 1.0, over 0.10 seconds, which is 10 kilogram meters per second, which is 10 kilogram meters per second squared. 10 kilogram meters per second squared. And now we're asked, what is the, so that's the rate of change of momentum. And what is the force applied? Well, let's see. We have J equals average force times the time. So the average force is the impulse divided by the time. It is equal to the impulse divided by time, which was, we said, 1.0 divided by 0.1, which works out to be 10. 10 Newton seconds per second, which is 10 newtons. That is the average force. Now, it is no coincidence, and no coincidence at all, that these two are equal to each other. So what we're seeing here is that force is the rate of change of momentum. And it turns out the definition of force is the rate of change in momentum, or delta P over delta T. Now let's just look at this a little more closely. We have this over here, which is the average force is the rate of change of impulse. All right, so if the average force is the rate of change in impulse and the impulse is equal to the delta P, then the average force is delta P over delta T. So we see it through the numbers, but we can also see it by just pure deductive reasoning here. That if J is always equal to the change in momentum, the impulse is always equal to the change in momentum, then J over delta T is delta P over delta T. And this is the definition of average force, the rate of change in momentum. Now, lastly, let's consider two sophisticated graphs. We will start out with a momentum time graph. And we'll do our Oy-Zerga. So we make our 0 there, our y-axis momentum, our x-axis is time. The intercepts will hold on for that since we're plotting them, not reading them. What we can read is momentum time, the axes. The gradient is delta P over delta T. So the slope of this graph is the force. In the area is momentum times time, which we said is, so if we look at the units, it's kilogram meters per second times second, so it's kilogram meters. It's like mass times delta x, which isn't really a quantity that we have meaning for. But we know the average force is the slope. So if we go back to our initial situation, we know we had an initial momentum of 2 kilogram meters per second. So let's make a 1, 2, and a 3 like this. So we had an initial momentum like this, and it's moving along minding its own business. And then the hand comes in and interacts with it for a certain period of time. This delta T, which we learned was a tenth of a second. So this is 0.1 seconds. That's what that is. And after that 0.1 seconds, we have a momentum of plus 3. Now, if we were to connect these two, this assumes that what I've drawn is a constant force, a constant slope. So this says the force is constant. Now, we saw in our previous lesson that with a change in momentum that we could have drawn it this way, depending on how it's behaving, or we could have drawn it this way, but the result is the same. The result is the same. So we could replace either red or blue dotted lines with the solid red line. And the solid red line is the, let me just undo that. The solid red line is the average force. The force may actually be doing something different, as we saw with compressed balls. We may see that actually the amount of force, oh, wait a minute, the slope is the force. What we saw is a small slope means small force, and as the ball gets more and more compressed, that force gets larger and larger, and then as the ball starts to expand, the force becomes less and less until it goes to 0. The force is the slope. Now, that was the case of a ball. This particular case is a hand pushing the cart, which is a much more reasonable assumption to make that the force is constant. And so that's why it makes better sense in this case for it to be a straight line. Now, our force time graph. So we have force and time and our Oy-Zerga. Origin will set to there. Y-axis is force, x-axis time. The intercepts we won't know yet because we're going to be drawing them. We can read force and time. The gradient is dividing the axes delta F over delta T, which anything divided by delta T is always the rate of change in that thing. So it's the rate of change in force. And the area is F times delta T, which we recognize as the impulse J. So the area is the impulse, which happens to be equal to the change in momentum. So we have a force that is not applied until after a period of time has occurred. And in fact, that force I'm just bringing these timelines down here so we can see how that connects to the momentum time graph. There is no force being applied on the cart. The cart's just moving, so there's a zero force up until the hand comes into play. And then there is a force, which we said was constant based on the graph above. The graph above, we said constant slope, which means constant force. Here we're showing constant force. And then when the hand is no longer pressing on it, we have zero force again. So we show no force up until the certain amount of time, and then we apply that force for 0.1 seconds. And it's during that time, that force is being applied during that time that we see an impulse. So that impulse, we said, is the area. And we already calculated what the impulse is. We know the impulse is equal to the change in momentum, which is 1 kilogram meters per second. Impulse and change in momentum. So that means that the area must be equal to 1.0 kilogram meters per second. And let's see, the force we said was 10 newtons. And we've got 0.1 seconds. So that means that the area of this graph is the impulse. These are two standard graphs. Notice how we use the Oizerga to pull out very, very important information and the connections between these two graphs. So that concludes our introduction to impulse. And in our next episode, we are going to look at the rate of change of momentum over time in more depth.